The hunt continues for the mathematics behind computers. In this video, we're going to examine division as an integer operation similar to what you did in your elementary math classes before learning about decimals. This is a cornerstone in modern cryptography, so you should become familiar with it. More importantly, in this video, we will use integer division as a backdrop to begin teaching about proofs and algorithms, some of the most fundamental parts of discrete mathematics and extremely relevant to how computers work. First, let's look at division by integers. The way integer division works is if we have two non-negative integers, n and d, and d is not 0, we can plot the multiples of d on a number line until we reach n. The number of d's until we reach n is the quotient, or q. So every division problem where d goes into n evenly can be rewritten as q times d equals n. Of course, not every division problem works out so neatly. Often, n will lie between two multiples of d. When this happens with integers, we use a term r, or the remainder, to make up the difference. So, our formula now has an r term added to it, and if our division works out, there is still an r. It's just equal to 0. We'll call this definition of division Theorem 1. Theorems are just a way to name something, so we can reference it later. A little syntax we also need to familiarize ourselves with is when r is 0, we say that d divides n using the pipe character. If r is not 0, then we say d does not divide n, using a pipe character with a line through it. With just that little bit of formality, we can now begin looking at proofs using integer division. First, let's prove that if a divides b and a divides c, then a must divide b plus c. First, because we know a divides b, we can rewrite the problem as b equals q times a, and we'll call it qb to show it's the q associated with b. We can do the same thing with c and get c equals qc times a. Now, using our new definitions of b and c, we can rewrite b plus c as qb times a plus qc times a. We can then distribute out the a, and we have a times qb plus qc, which is guaranteed to be divisible by a. Thus, because we can write b plus c as a multiple of a, we have proven that a divides b plus c. This is a fairly standard proof technique, using variables to demonstrate some property of how the variables interact. And because we didn't use a real number like 7 or 22, we can say that this divisibility rule holds for all integer numbers. Another nice thing about proofs is that once we have a proof, we can use it to say other things with a bit of hand-waving. For example, by the same logic of the addition proof, we can say if a divides b and a divides c, then a divides b minus c when b is greater than c. We can even generalize a bit and say if a divides b or a divides c, then a must divide b times c, because once again, as long as one of the components has a factor of a, then the entire product must be divisible by a. Furthermore, we can also demonstrate the transitive property, where if a divides b and b divides c, then we know that a must also divide c. Because a divides b, we can rewrite our problem as b equals qb times a. And because b divides c, we can rewrite our second problem as c equals qc times b. So, we replace the b with qb times a, and the product must then be divisible by a. We'll call this collection of rules for divisibility Theorem 2. Next, let's look at the prime numbers. Prime numbers are a special case of divisibility because they're a set of positive integers that can only be divided evenly by themselves and the number 1. Any other number will have a remainder of r greater than 0. To determine if a number n is prime, we can use a mathematical algorithm. First, we check if n is 2. If it is, we know that 2 is a prime number. If n is not 2, then we check if 2 divides n. If it does, then we know n is not prime because a number other than n and 1 divides it evenly. This removes all other positive even integers from consideration. The next step is to calculate the square root of n and round down to the nearest integer. We'll call it k. Finally, we check d divides n, where d is any odd number greater than 1 and less than or equal to k. If r is ever 0, from this series of calculations, we know that n is not prime. Numbers that are not prime are called composite. That is to say, it can be written as a multiplication of other numbers. Taking a question, like is a number prime, and breaking it down into simple steps that only need to be repeated a large number of times, is a core principle of algorithms, and is one of the crucial steps needed to make computers work in the way we're all familiar with. For our last example, we're going to look at a proof that deals with divisors and an algorithm to calculate them. Let's say we have two numbers, a and b, and there is a third number, k, which evenly divides both numbers. We call k a common divisor. For example, every positive even number has 2 as a common divisor because 2 divides all positive even integers evenly. What we're interested in is calculating the greatest common divisor between two numbers a and b. This number comes up all the time in cryptography and when calculating cycles. Our third theorem, and what we will prove, will be the following. If d is the greatest common divisor of a and b, then d equals s times a plus t times b, for some integers s and t, not necessarily both positive. And if some number c divides a and c divides b, then c divides d. That is to say, all common divisors of a and b will also divide the greatest common divisor, d. First, we'll define x as the smallest possible integer that can be written as s times a plus t times b for some integers s and t. Next, we'll use our addition rule in Theorem 2. Since c divides a and c divides b, we know that c must divide x because we have defined x to be the sum of a times s, which is divisible by a, and b times t, which is divisible by b. This demonstrates that any divisor of a and b will divide x, which is the second part of our theorem. Now, we need to show that x is a common divisor of a and b. This will make x the greatest common divisor of a and b because it divides both a and b and is divisible by every other divisor, c. To show this, we can use Theorem 1. Because x divides a, we know that a equals sum qx plus r. We can then rewrite this as r equals a minus q times x. Next, we can substitute x with the original formula s times a plus b times t. We can then distribute the q. Finally, let's factor out a and b. Let's examine this last statement. Every variable is an integer, so we've managed to loop back to our original formula. An integer, r in this case, is equal to an integer times a plus an integer times b. Now, if r doesn't equal 0, then we have a contradiction, because we just defined x as the smallest positive integer that satisfies the first part of Theorem 3. Thus, r must equal 0, and when r equals 0, that means x must evenly divide a as per Theorem 1. We can use the same logic to demonstrate that x must also divide b. Thus, our Theorem 3 must be true. So we've proven that d in our Theorem 3 is the greatest common divisor. Now let's see how we can use an algorithm for calculating it. We will be using the Euclidean algorithm. First, we organize the problem so that for the GCD of a and b, a is greater than b, and b is greater than 0. Next, we divide a by b and get our Theorem 1 formula, some integer q1 times b plus some remainder r1, where q1 is a positive integer and r1 is greater than or equal to 0 and less than b. Two things to note here. First, we can rewrite our equation to be r1 equals a minus q1 times b. Secondly, by using our Theorem 2 subtraction rule, we know that a divisor of a and a divisor of b must divide an integer equal to a minus b, which r1 is in this case. So we can now write the GCD of a and b is equal to the GCD of b and r1. This is the algorithm, and the next step is to solve for b. So we get b equals some integer q2 times r1 plus some remainder r2, where r2 is greater than or equal to 0 and less than r1. We then continue our algorithm until we have no remainder. The Rn of the last step is the GCD of a and b. Let's look at an example using numbers instead of variables. We'll calculate the GCD of 190 and 34. First, 190 divided by 34 equals 5 times 34 plus 20. So our new problem becomes the GCD of 34 and 20. 34 divided by 20 equals 1 times 20 plus 14. This becomes 20 divided by 14, which becomes 1 times 14 plus 6. This becomes 14 divided by 6, which is 2 times 6 plus 2. And finally, 6 divided by 2, which becomes 3 times 2 plus 0. Because our remainder is 0, we know that the previous remainder of 2 is the GCD of 190 and 34. Feel free to try this algorithm with a few other numbers to get a good feel for it. There will be some problems to try under this video. The final thing we'll look at today is the modulus or modulo. This is how computers calculate the remainder of integer division. Using Python syntax, integer division is a double slash, and modulus is a %. So you might see 25 modulo 4, which is equal to 1. A more complex example is Say the time is 5 o'clock, and we want to know what time it will be in 137 hours. We can simply add 5 and 137 to get our total hours, and then modulo by 12 to get 10 o'clock. If you want to implement the algorithms we talked about in the video, this is how you can do it in Python. Division is something you were familiar with before this video began, but you now have a more formal perspective of it than what you saw in your elementary arithmetic class. The two main takeaway ideas from this video are, firstly, that we can solve mathematical problems by chipping away at them one step at a time using algorithms, and that by transforming problems using rules we either know or derive, we can make further interesting conclusions about the problems we're working on using proofs. These two concepts are the beating heart of computer science: algorithms to complete tasks, and proofs that confirm no matter what inputs we give to our algorithm, it will always behave the same way. These are complicated topics, both of which can fill years of study. You're a long way from completely understanding the math that goes into a computer, but I want to congratulate you on taking another step forward with discrete mathematics.